I am Sivakumar, Assistant Professor of Mathematics. I am having 20 years of experience in engineering colleges. Today we are going to discuss a lecture on continuity and differentiability. So in previous lecture I have discussed the importance of mathematics and what is mathematics, and after that what is engineering mathematics, followed by limit of a function and continuity of the function, and we have discussed types of discontinuities. Now today we are going to discuss what is a continuity and what is a differentiability of functions of single variable. In the coming lectures we are going to discuss limit, continuity and differentiation for functions of two variables, followed by limit, continuity, differentiation and integration, all four calculus topics for complex functions. Right now in this video we are going to discuss continuous functions and differentiable functions. Then necessary and sufficient conditions we are going to discuss, because in order to understand any theorem statement we need necessary and sufficient conditions. And when we can say a condition is said to be necessary, when we can say a condition is said to be sufficient. These two things we are going to discuss, and that is useful in order to understand any theorem in any concept. Next, followed by, there is a important relation between continuity and differentiability that is established by this theorem, which is nothing but every differentiable function is continuous. And all these things we are going to discuss with a pictorial representation and graphs and Venn diagrams. Watch the video till the end. If you like the video, share the video to your friends and tap on the bell icon for getting more updates and for the coming videos. Now we discuss what is the definition of continuity of a function at a point, and what is the definition of differentiability of a function at a point. So we know that limit x tends to a, f of x is equals to f of a. Already we have discussed this definition. So here I said 3 points. Limit of a function f of x exists at a point a, and the function value exists at a, both are equal, then we say function is said to be continuous. If both are unequal, then that is discontinuity of first kind. If limit does not exist, that is called discontinuity of second kind. Discontinuity of first kind is nothing but removable discontinuity. Discontinuity of second kind is jump discontinuity, because function takes jump via a if limit of the function at a does not exist. So now coming to the differentiability of a function at a point, we know that differentiability of the function at a point. So limit x tends to a, f of x minus f of a by x minus a. Rate of change of function with respect to change in x is known as differentiability, and it is denoted by f dash of a, which is a principal formula for derivative. So if we consider dy by dx, so that is nothing but limit delta x tends to 0, delta y by delta x. So this one we can write limit delta x tends to 0, y plus delta y, just I am adding y here, y plus delta y minus y by delta x. So if we consider x axis, y axis, let us consider a point here, x comma y, and with a small change in x, let us consider this is delta x, and a small change in y, that is considered delta y. So this is the given function. Let us suppose that y equals to f of x. Now how far the function is changing in y direction? For small change in x direction. So if you consider a chord joining these 2 points, so this is nothing but x comma y point, and this is nothing but x plus delta x comma y plus delta y. If you extend, if you extend this line here up to here and up to here, and we know this length is x and this length is y, and this small length is delta x, and this is delta y. So this total length is going to be y plus delta y, and this total length is going to be x plus delta x. That's why this point we are indicating like this, x plus delta x comma y plus delta y. Now slope of this chord joining these 2 points is given by y2 minus y1 x2 minus x1. So that is y plus delta y minus y by x plus delta x minus x. So if we cancel y and x terms, we got delta y by delta x. And if this delta x is negligibly small, then this point is almost near to this point, which means this chord is going to be, so this is the curve like this, and this point approaches this point as delta x tends to 0, means this chord, whatever we have drawn, is going to be tangent at this point. So that's why first order derivative of a function at a point gives the slope of the tangent to the curve. Now we have to discuss what's the relation between continuity and differentiability. Before going to see that relation, we have to discuss what is a necessary condition, what is a sufficient condition. Not only for the theorem, what we are about to discuss, every differentiable function is continuous. For every theorem, necessary and sufficient conditions are required. So first we discuss some examples for continuous functions and differentiable functions. For example, if we consider a Venn diagram for continuous functions and differentiable functions, let us consider continuous functions here. So any point if we just consider here within this circle, a simple closed curve, so that is a continuous function. Now if we consider differentiable functions in another set, so this is a set of differentiable functions. This is the set of continuous functions, this is a set of differentiable functions. Now I am writing some function f1 here, which is not continuous, therefore it is not going to be differentiable. If I write some function f2 here, which is continuous but not differentiable, and if I write some function here f3, which is a differentiable function, therefore it is going to be continuous functions. So three things here we have to discuss. What are the functions which are not continuous like f1? What are the functions which are continuous but not differentiable like f2? What are the functions which are differentiable? If any function is differentiable, definitely it is going to be continuous. So if you take any function here, it is differentiable function, therefore it is going to be continuous function because this dot is within both sets. Now if you consider any dot here, that function, I mean if you suppose that this dot is some function, that function is continuous but not differentiable. And if you consider any function here which is not continuous, which implies it is not differentiable. So these are the things we are going to discuss and explore with different examples now. Now we discuss necessary and sufficient conditions. For example, if you consider a conditional statement, if P then Q. So here P and Q are two statements, and this conditional statement we can write P conditional Q, and if it is tautology, I mean it is true for all cases, then same thing we can write like P implies Q. So here if you consider any theorem statement, that will be in this form, if P then Q. Every differentiable function is continuous. We can express that by means of predicates. Statement calculus and predicate calculus are more important in order to understand any theorem. So for example, coming to the statement calculus, if we consider P conditional Q is the given statement, and its converse is known as Q conditional P. Q implies P. And we can write its inverse. Inverse is nothing but negation P implies negation Q. And contrapositive is negation Q implies negation P. So if we construct the truth tables for all these four, statement always congruent for contrapositive. Converse is congruent for inverse. If we discuss only this part, instead of proving a statement, we can prove contrapositive because both are one and same. So here, if we consider if the statement, conditional statement P implies Q, that we can write like this: if P then Q, or Q if P. P is sufficient for Q, Q is necessary for P. So, if you consider any conditional statement or any theorem statement is in this form, if P then Q, we say P is said to be sufficient condition. If we have condition in place of P, which is called hypothesis, we can say generally, so that is a sufficient condition. And if we say some condition is in place of Q, which is known as conclusion, and this is said to be necessary condition. We have a condition in the conclusion place, in place of Q, there is a necessary condition, and this is said to be sufficient condition. Now we discuss the theorem which establishes relation between continuity and differentiability. So that is every differentiable function is continuous. So that we can write if we consider any function f of x, a function of single variable which is differentiable, then it is going to be continuous. If you consider any function which is differentiable, then it is going to be continuous. You can write like a P implies Q, or if f of x is differentiable, then we say f of x is continuous. So by means of Venn diagram you can write like this. So this is a set of differentiable functions and this is set of continuous functions. So if we consider any function in place of f3, so that is within this set f3 is a differentiable function, therefore it is continuous function. f2 is continuous but not differentiable. f1 is not continuous. So if we consider this is the statement, means differentiability is said to be, this is in place of, we already discussed the necessary and sufficient conditions. P is said to be sufficient condition and Q is said to be necessary condition. Means f of x is differentiable, that is sufficient in order to say f of x is continuous, because differentiability we have in the hypothesis. The condition of differentiability we have in the hypothesis. Therefore, differentiability is sufficient to say function is continuous. Continuity is in the necessary part, that is in the conclusion. Continuity is necessary condition for differentiability because continuity we have in place of Q. See,
From this, we can write the contrapositive, that is negation Q implies negation P. Why we call Q is necessary? It's very clear that P is sufficient. From P itself, we are getting Q without having or without knowing any extra data. So from P itself, we can get Q. That's why P is sufficient. It is clear. And in order to know why Q is necessary, which is in conclusion, we have to consider its contrapositive. The contrapositive statement is nothing but negation Q implies negation P. Without Q, we cannot get P. Without Q, we cannot get P. Means Q is necessary. So here, the same statement we can write like its contrapositive. If f of x is not continuous, then f of x is not differentiable. If f of x is not continuous, then f of x is not differentiable, which means that continuity is necessary. In order to say a function is differentiable, continuity is necessary. Without continuity, we cannot get differentiability. That's why continuity is a necessary condition for differentiability. Differentiability is a sufficient condition for continuity. So that we can know just by knowing this fact. P implies Q, where P is sufficient for Q, Q is necessary for P. For example, if we consider some examples of these functions f1, f2, f3, the functions which are not continuous, I can write f1, sawtooth wave we can consider, sawtooth wave, the graph of sawtooth wave we can draw like this. So it's a straight line up to some time, and after that it suddenly falls to 0 again. The same, it is a periodic function. So this is the sawtooth wave, and if you see at these points, function is taking jump, means function is having jump discontinuity. Left hand side limit, this is the left hand side limit value, which is different from right hand side limit. Here the function length is very small, and here we are having some value for the function. Function is taking jump down here for every interval t, we can say, means it is having finite number of finite discontinuities, or we can say finite number of jump discontinuities. It is a piecewise continuous function, but not continuous function. If it is not continuous function, it is not going to be differentiable. So best example for f1. Another example for f1, that is a square wave. It's a constant function up to here, and after that it jumps down, and here again it's jump up here. This is a square wave, because this part, if you observe, this is a square. That is just one example. I can say switch on some light for some time and switch off for the same time and switch on for the same time. So that kind of signal is this. Now it's having jump discontinuities. So this is also not continuous. This is a piecewise continuous. This is constant function. It's a continuous up to here, and it's a continuous up to here. But here it is having a finite jump, and here also it is having finite jump. Discontinuity of second kind. So it is a piecewise continuous function. Therefore, it's not differentiable, of course, and it is going to be continuous in this interval. Therefore, differentiable. But at this point, it is not continuous. Implies it is not differentiable. Next, f2, which are continuous but not differentiable. f2, continuous but not differentiable. For example, if we consider modulus x graph, modulus x graph is like this. So it is a continuous function, but it is not differentiable at this point. Modulus x definition, we know that is x when x greater than 0 and it is minus x when x less than 0. In place of modulus x, if we just replace, that's a function value, y equal to x line, this is y equal to x line and this is y equal to minus x line. Slope of this line is 1 here, slope of this line is minus 1, left derivative is different from right derivative at 0. At 0 minus it is having slope minus 1, at 0 plus it is having slope plus 1. Slope means that gives the derivative. So if you differentiate x, we get 1 here. If you differentiate x here, minus x here, we are going to get minus 1. It's not differentiable at 0 because the function is having a sharp turn at this point. If you want to say any function is differentiable, it should be smooth. We can able to draw the tangent at that point. Then only we say function is differentiable. So we are unable to draw the tangent for this curve at this point, means it is not differentiable function. But it is a continuous function. So this is the best example. Modulus x is the best example where the function is continuous but not differentiable. Now another example we can give a triangular wave. Triangular wave. We can consider triangular wave is a periodic function. We can consider a straight line like y equal to x, and after that with the negative slope another line like this, and here if you see at these short terms the function is not said to be differentiable because we are unable to draw the tangent. It is very clear that if the curve is having unique tangent at each and every point, then the function is said to be differentiable function. If you see the sine graph or cos graph, sin x graph, if we see sin 0, 0, sin pi by 2 it is 1 and sin pi is again 0. So sin pi by 2 is 1, again sin pi is 0, sin 3 pi by 2 minus 1, sin 2 pi 0. So like that, it's having a smooth curve at each and every point. We are able to draw the unique tangent for the curve, which means that function is differentiable, and we know that derivative of sin x is nothing but cos x. So we have discussed the functions which are not continuous like f1 and the functions which are continuous but not differentiable like f2 and the differentiable functions f3. For f3 we can give so many examples: sin x, cos x, or any polynomial in x. E power x, log x, except x is different from 0. All these functions are differentiable functions. If any function is differentiable, means that is going to be continuous. There are some functions which are continuous but not differentiable, like modulus x and triangular wave. If any function which is not continuous, then it is not said to be differentiable. So this is the relation between continuity and differentiability, and the important theorem that every differentiable function is continuous like f3. If you consider any function which is differentiable, definitely it is going to be continuous. Thank you so much.